Welcome students. Today we will study the proof of Taylor's theorem. What Taylor's theorem states that if a function fz is analytic at all points inside a circle C with its center at A and radius capital R, then at each point Z inside C we have f of z is equals to f of a plus f dash a z minus a plus f double dash a upon factorial 2 z minus a to the whole square plus dot 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 plus f nth derivative upon factorial n z minus a to the power n plus dot dot dot. This is minus. Now proof of this particular theorem. This theorem is very important in complex analysis, and for going in the proof of this particular theorem, let's draw a region, a circular region bounded by circle C whose center is at A. Let us draw another concentric circle C1 inside C with center at the same point, and point Z lies inside both circle C and C1. A point W lie on this particular C1 we would pursue as follow. Take any point Z inside C and C1 where C and C1 are concentric circle. Concentric circle means center of both circles are same at A, and W be any point on C1, then 1 upon W minus Z. W is the point on C1 and Z is the point lie inside C1, can be written as 1 upon W minus A plus A minus Z, which is equals to 1 upon W minus A minus Z minus A, which can also be written as, if we take W minus A common, then it would become 1 upon W minus A within bracket 1 minus Z minus A upon W minus A, bracket close. Here Z minus A is less than W minus A modulus of both. This implies that Z minus A upon W minus A is less than 1, which is a basic condition for binomial expansion. So this expansion can be written as 1 upon W minus A 1 minus Z minus A upon W minus A to the power 1 minus 1, as Z minus A upon W minus A is less than 1. Therefore we can make binomial expansion of above, and it would be 1 upon W minus A within bracket 1 plus Z minus A upon W minus A plus Z minus A upon W minus A whole square plus Z minus A upon W minus A whole cube plus n dot dot dot. W minus a is outside of this whole bracket, so we can also write this as 1 upon W minus a plus z minus a upon w minus a to the whole square plus z minus a whole square upon w minus a whole cube plus z minus a whole cube upon w minus a whole 4 plus dot dot dot. Now this is equals to 1 upon w minus z. As we know, z minus a upon w minus a is less than 1. This means that this whole series is a convergent series. If this series is uniformly convergent, so it can also be integrable. Means this particular expansion is convergent as well as integrable. So multiply this series 1 multiply 1 with fz with f of w and integrate with respect to w. We will get fw upon w minus z dz dw integral is equals to f of w upon w minus a dw integral plus integral, let's see, f of w z minus a upon w minus a dw plus dot dot dot, which can also be written as simply integral f of w upon w minus a dw plus z minus a integral f of w upon w minus a whole square dw plus z minus a integral f of the whole square integral fw upon w minus a whole cube plus dot 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 dot, and all these integral is over this bounded circle C1. So limit would be C1 C1 and C1 C1 C1, and left hand side of this particular expansion is equals to integral f of w upon w minus z dw. Now by Cauchy integral formula, we know that integral f of z upon z minus a dz is equals to 2 pi I times f of a. This is a basic formula, Cauchy integral formula. We use this particular formula in the above expansion. If we generalize this particular formula, then f of z upon z minus a to the power n plus 1 is equals to 1 upon factorial n times nth derivative of f at the point A. If we use this particular formula, we would get values as follows of our expansion as follows: integral f of w upon w minus z dz, this over c1, this would be equals to 2 pi I times f of z. Again, integral f of w upon w minus a dw, this would equals to 2 pi I times f of a. Again, f of w upon w minus a whole square dw is equals to 2 pi I f dash of a over c1. f of w upon w minus a whole cube dw is equals to 2 pi I f second derivative a upon factorial 2, and so on. So substitute all these value in above equation, we will get f of z is equals to f of a plus f dash a times z minus a plus f double dash a upon factorial 2 z minus a whole square plus f triple dash upon factorial 3 z minus a whole cube plus dot dot dot, and nth term would be fn upon factorial n z minus a to the power n plus dot dot dot. This particular statement is known and represented as Taylor's theorem. And this is the proof of Taylor's theorem, which is very important. Once again, we'll go through what we had done. To prove this particular results, let's draw a region centered at A point Z lie inside C1. Let's consider another point W which lie on this C1. Then 1 upon W minus Z is equals to this much, can be represented as this much, 1 upon W minus A within bracket 1 minus Z minus A upon W minus A. Now this Z minus A upon W minus A is less than 1 because the Z minus A is this distance and W minus A is this distance. This distance is greater than this small distance, therefore Z minus A upon W minus A is less than 1. So we can apply binomial expansion. Binomial expansion, after applying binomial expansion, we would get this as an expansion, as this is uniformly convergent because terms is less than 1. Therefore, we can multiply this with Fw and integrate with respect to W. We would get this particular statement. Now apply Cauchy integral formula, we would get our required result, which is Taylor's theorem. Hopes you understand this particular proof of Taylor's theorem. Thank you.